Thank you, Daria. Thanks for having me as well. So today I'm going to go over not all of these TLAs or three-letter acronyms on the screen here, but the three in particular are the SLOs, the service level objectives, the SREs, which I hope everyone knows is the site reliability engineers or engineering, and then the third one is GHGs, which stands for greenhouse gases. But first, I'll tell you a little bit about myself. I am a principal engineering manager over at Microsoft. I also sit as the chair of the Patterns Working Group at the Green Software Foundation. And then when I'm not behind a computer screen, I'm typically out running on the roads or mountains. And then somebody called this out. That is supposed to be a cloud of me running fast, not anything else. So, cool. So I'm going to start with a question of how much energy does your system consume? Do you even know what that number is if you had to answer it? Is it a lot? Is it a little? Do you have a comparison between it? You know, just knowing the total number is important, but what about per user or per request or per each gigabyte that you have stored in your system? How much energy is being consumed to do that, whatever it is that your system needs to do? And also, not all energy is created equally. So this map here is a map of Europe, but it's also, the colors are showing the various carbon intensities of the electrical grids in those areas. This is a site called Electricity Maps. It's open for anybody to use. They have an API. You can access this data. The green colors there are lower carbon intensity, so I'll call out Scandinavia is a great area. They're using a lot of hydropower, wind power, so their carbon intensity is lower. And Poland, for example, is one of the darker ones there, has a lot of gas and coal. So when it's not windy and it's not sunny, all of these electrical grids need to offset that energy with something else. And so they'll use typically something that's a little bit dirtier like coal or oil or gas. So carbon intensity is how much carbon is emitted to generate 1 kilowatt hour of energy. So you can see how all that is not necessarily created equally. And then the other thing I'll touch on here is what's called CO2 equivalent. Whenever I say carbon in this talk, or I'm talking about carbon or emissions, I'm really talking about CO2 equivalent. And what that means is it's just a way that we normalize all of the greenhouse gases that are available. So they all act a little bit differently. For example, CO2, when it's emitted, carbon dioxide, stays in the atmosphere for roughly 40 years, whereas something like methane, it only stays in the atmosphere about 10 or 12 years. But it's a lot more potent when it goes up there. And so CO2 equivalent is just our way of normalizing across all those different gases. So carbon just means CO2 equivalent on this. And then the other thing, Namrata, the talk right before this, if you just joined or you're watching the video later, Engineering for Sustainability from Namrata was really good before. She went into this as well, but I'll touch on the scopes of carbon. The first one is your scope 1 is how you measure it. These are your direct emissions, the things that you directly put out into the air. If you're burning coal on your own home power plant or something like that, those are your scope 1 emissions. Your scope 2 is anything that's purchased, so your own electrical grid where you're currently operating. It's typically location-based. And then that scope 3 is essentially all of the other emissions that are there. That's, if you think of a computer or a server or a phone, it's the rare earth materials that needed to be extracted, the emissions that went into that. It's the factory that put it together. It's the shipping to get it to the store or to your front door. It's the packaging it came from. It's even the disposal of the phone or the laptop after it's done being used. All of that is factored into your scope 3. It's everything else. So you can understand why that's typically the largest one. We also call that embodied carbon. So it's how much carbon is embodied in the thing that you're trying to use. So great. I mentioned I work with the Green Software Foundation. We came up with an equation here to measure the carbon intensity of your software, which we shorten to SCI, or software carbon intensity. And this equation's pretty basic and straightforward, but to get the information sometimes can be a little tricky. So I'm going to walk through this equation here. The E here stands for the energy. It's the total energy consumed by your system. That's measured in kilowatt hours is the unit for that. The I is the carbon intensity. So that big colorful map that we showed was what is the intensity in that grid for your system itself. M is the embodied carbon, so how much went into it. Essentially, that's scope 3 to create that thing, that server, whatever it is that you have. And then the last one here is, again, more of a normalization, is to say, well, what is the rate? How does your system scale? Do you scale by users? Do you scale by requests? Do you scale by something else? That's essentially how you normalize all of this information. So we're going to run through an example here. I'll keep it pretty simple for this scenario, but you can certainly go as deep or as complex as you want. This equation will support it. So let's start with the E, the energy consumed. For this scenario, we'll say we're running a single machine at 50% capacity or load for 24 hours. Now, you can break that down into smaller detail than 24 hours if you want, but we'll just keep it simple here. So this is the general equation you need to fill out. You take the CPU power consumption, how many CPUs you have, add that to the memory power, and then add on any GPU consumption that you may have in your system as well. For my very simple scenario here, we'll stick with Azure since I'm at Microsoft. We'll pick a VM, let's call D8AS-V4, that VM. I know from the Azure documentation that that's running an AMD EPYC 7452 processor, and then I know from the AMD documentation on their site that that processor has a 155 watt TDP, stands for thermal design power. And so to calculate your power consumption now becomes pretty easy once you have that TDP value. You can just say that it's the TDP times the load times the time, so how many hours you have since we're in kilowatt hours. To make the units work well, it ends up being 1.86 kilowatt hours over that 24-hour time period. So we've got 8 CPUs in there, so we multiply that by 8. Memory power is essentially nothing in this scenario, so we can call that 0 to simplify it, and this doesn't have any GPUs on this machine. So again, simple scenario here, but you can add your own complexity into there. So that works out to be just under 15 kilowatt hours. If we move on to I, that's going to be our carbon intensity. We can, being in a cloud, being in Azure, we can put it in any region we want. Since we're in Netherlands today, West Europe is also based in the Netherlands, and so let's use that one. So over a 24-hour time period, this was maybe 2 or 3 days ago, I think. You can see, again, this is from that Electricity Maps site. Over 24 hours, you can see how they had to add more coal and gas power to offset when it was not windy or sunny. And then in the last 6 hours or so of this graph, it became a lot more sunny and windy, so their carbon intensity goes down. So over that 24-hour time period, you take the average, it's 265 grams of CO2 per kilowatt hour. All right, and then now we move on to the M, the embodied carbon. So again, we have just this single VM over a 24-hour time period. The cloud carbon footprint, which is on GitHub, open sourced, separate company than any of the public clouds, has gone through and done a lot of this math for you. It's in a giant spreadsheet that you can scroll through and find. So I'm able to find the D8AS V4 VM, and we can see that it's 1,560 kilograms is their embodied carbon, is how much carbon was needed to create that VM, that virtual machine. If you assume, let's say 5 years is how long a server will last in a cloud, roughly, then it's just a quick math problem to say, what is 24 hours worth of 5 years? And that ends up being 855 grams of CO2. And then the last piece here is for the rate. We're going to use requests, and we're going to say that this system runs 10 requests per second. So not super fast, but fast enough. Pretty good load. That works out to 864,000 requests in a 24-hour time period. So we go back, we'll plug all this stuff in, do the math on all of that. It ends up being that number, your emission rate per request. I don't think that number looks pretty enough, so we're going to multiply by 1,000 requests, and we'll say that this is now our carbon emission rate per 1,000 requests of this system. So that one machine, 5.553 is your emission rate for your system. So when you think about this as an SRE, this is now your SLI. This is your service level indicator. You can start to create SLOs around this number based on whatever your business needs or your business scenarios are. And so this is how you take sustainability and make it part of your SLOs, part of your reliability conversation. But any good SLO, you got to be able to change it. So how do you start to reduce carbon emissions in your system? That 5.55 number, great, you want it lower. How much lower can you get it to do that math? So the good news is there's only 3 ways that you can reduce carbon emissions in your software. And those 3 ways are you can use less hardware, you can use less energy, or you can use the energy more intelligently that you have. So to use less hardware, that speaks to that embodied emissions part of the equation. So less machines is a really great, really easy one to do there. Less storage, so using your data retention so you're not keeping data around. Using more utilization of machines or extending the lifetime of the machine. We used 5 years as that number. If you can extend that to 6, 7, 8, that embodied carbon number stays constant. And so the longer you can use it, it reduces your overall intensity. Second one, using less energy. The VM that we used was 155 watts for TDP. There's certainly ones that are better. There's also ones that are worse, that need more or less power. A lot of the Graviton from Amazon is great, super power efficient. Anything ARM-based on CPUs now are going to be more carbon efficient. But things like code optimization, code efficiency, performance, those things will tie into less energy being needed or required for your system. And the last one, using energy more intelligently. You'll sometimes hear this as carbon aware, and this means that your system will react to the amount of carbon in the grid. So the carbon intensity map that we showed before, and we had that one time period where it was a higher intensity and the other where it was a lot lower. If you can delay workloads during the time where the intensity is high for an hour, 2 hours, 3 hours, whatever it may be, to a time when it's much lower, you're now going to be using the energy more intelligently. It's the same amount of energy, same amount of machines, but you're doing it at a time that's less intense. And so delaying those jobs until that time can allow you to be more carbon aware, using your energy more intelligently. You can also shift regions. Australia, for example, runs on a lot of coal. The east coast of the United States runs on a lot of coal, but the west coast runs on a lot of solar and wind and hydro. And so just moving your machines around, even within a geo, will be very useful and help you reduce your overall intensity. But why am I here talking about carbon at a site reliability conference in the first place? So for me, I see reliability as balancing operational and technical choices that we have to make as a business, as a system, as a service. Over time, all of those choices will impact the planet in some way. Since SREs are really focused on systems thinking, the biggest system that we all share is the planet. And so it's a really great alignment with SREs and this focus to also be focusing on this problem too. The largest coal-powered machine in the entire world is the internet. So this is front and center for all of the work that we do as SREs. By 2040, 15% of all emissions will come from software. That's the track that we're on right now. And so there's a huge problem that we all have a big hand in and can make a significant impact to. We need to start balancing our operational and our development work with the planet itself on these 3 different axes in order to find what is the right outcome for the work that we need to do. And over time, reliability becomes sustainability. But really, at the end of the day, for me, it's just having a habitable planet is the ultimate reliability challenge and the ultimate in reliability. So that's it. Thank you very much. Appreciate it.